Wow.
All right, we are now recording. We are live. Thank you, everyone who has come out tonight, as well as those that have come online. Tonight, we are going to be talking about our different SIG groups, our special interest groups. Starting off, we don't really have very much to discuss in terms of like board stuff, do we?
I don't think so.
I don't think so.
No.
Okay, so we'll just go ahead and get started into it. We have a couple of different people that are going to be presenting. For the most part, it's four people, correct?
Yeah, I think so.
4 people for our 4 different SIG groups, so they'll have about 15 minutes each. We're going to start in the obvious way with the beginners group. And I will ask, please, if you are unmuted, to please mute yourself. Okay, so I'm going to hand over to Don, our current president.
Okay. Let's go over this one. Can the people out there see the display that says Deep Sky Out next September?
Now they can.
Is anybody talking? Okay.
Yes, I can see it now.
Okay, great. Okay, so I started, this is what we used to, originally we called this just VSIG. Now we call it the beginner SIG or the visual SIG. I should explain that SIG means a special interest group, and the idea is that rather than just meeting monthly and having a speaker, we wanted to have smaller groups of people that was more interactive, rather than just sitting there and watching a speaker talk for 40 minutes, which is great. But we also wanted to have people getting together in smaller groups so that they could actually talk to each other and learn stuff and learn more directly, one-on-one and that sort of thing. And so we started putting these special interest groups together. The first one we just called VSIG. Now we call it the beginner SIG. It hasn't really changed much, but what has happened is we've added other SIG. We've added an astrophotography SIG, and we've added an advanced project SIG, and they we'll talk about those later. But for right now, this is we always start out the beginner SIG with sort of an overview of what's up in the sky for people who don't know, because there's a lot of people who are just getting into this and they don't know what to look at with a telescope. So we wanted to show people what they can look at, what's up right now, what's up tonight. So for September, we've got these 4 constellations: Andromeda, Pegasus, Cassiopeia, and Aquarius. So can we go to the next slide? I don't know. Can I switch it?
Yeah, you should be able to.
Yes, left.
Yeah, left. Is it on?
It's going to be one of those battery issues.
Great.
Go ahead.
I'll just
All right.
do it manually.
I think just fixed. There we go. Okay, so here we see roughly looking south. If you look due south, you can see Capricornus is right on that green line. That green line is called the meridian, and it's the dividing line between east and west. And so that's a kind of a key marker in the sky. So Capricornus, when things are on the meridian, that's their highest points that they're going to get in the sky. So that's why the meridian is kind of important to us. This thing's not quite working back here.
It's the left ear, Don.
What's that?
It's the left ear, not the right ear.
Okay,
Boom.
so hopefully it'll work a little better now. Okay, so and then we have down below to the lower left, we can see Pisces, Australis, and we also see Aquarius is the green circle up there. So we can go to the next slide. And then over here in the northern horizon, the northern sky, we can see Cepheus and Cassiopeia and Perseus is just coming up. Now, if you look at this, the stars are rising on the right side. The stars to the right are coming up. So those are the things that are coming up. One of the things I'll point out here is the star Algol. Algol is, I don't know if anybody else can see this, I guess not. But Algol is a very famous variable star that changes in brightness at very precise intervals.
Yeah.
Was I doing that pointer?
No, I was.
Okay. All right. So anyway, we go to the southeastern horizon, we look at Aquarius and Capricornus. These are really faint stars. If we look at this one constellation, Fomalhaut or Fomalhaut, magnitude 1, that's not too bad. That's pretty bright. Deneb Algidi is magnitude 3. That's pretty faint. And then it gets fainter from there. But there are some nice things up there, like the Helix Nebula. The Helix Nebula you see in the lower left, that's the biggest planetary nebula in the sky. It's the closest to us. Hubble has produced a really famous image of that. Sometimes it's called the Eye of God Nebula. I think fanciful names, but it's called the Helix Nebula typically. And then there's a globular cluster. Now, globular clusters are like galaxies, except that they're just, it's like a ball of stars, but they kind of look like galaxies. And then NGC 7009, the Saturn Nebula, that's a really neat object because it's really an intense blue. And when you look at some of these objects, you don't see a lot of color. Like that Helix Nebula is glowing in this beautiful red color. Well, you don't see that visually through a telescope. You can take pictures of it and get that to come out. But the Saturn Nebula really is that color. When you look at it, it's really a brilliant blue. And then M72 is another globular cluster that it looks very similar to all globular clusters. But anyway, am I pushing the wrong button here?
It's the right button. What? I just switched.
Okay. So anyway, so then going to the next slide, Pegasus and Andromeda. Pegasus is the square of Pegasus is a very famous asterism, a very famous formation up in the sky, and so anyway, Pegasus and Andromeda are both very, very prominent, and they've got some really nice objects in them. So you can see a couple of galaxies here, 7479 and 7331. You can also see the map up here, the little circles. What I do when I make these maps is I always highlight the Messier objects and the Caldwell objects. Go to the next slide.
Yes. Sorry, I was.
Okay, so when you're looking at Andromeda, one of the things that's most outstanding is the Andromeda Galaxy. This is an enormous galaxy. It's one of our I don't know if it's the closest galaxy to ours, but it's one of the closest. It's the closest large galaxy, and it's really quite stunning. When you look at this galaxy, to give you a certain sense of scale, it's 3 degrees long. So from the faintest part of the upper left to the faintest part of the lower right, that's about 6 full moon diameters. And it's about the width of a full moon. So it's about half a degree wide and 6 full moons long. Okay, next one. Anyway, oh, one more thing I was going to say. Can we just go back to that? All right. So the other thing I was going to say about this is if you have a large enough telescope, one of the things that's interesting is you can actually see globular clusters in the Andromeda Galaxy. And so I pointed out a couple of them here, but I think there's 20 or 30 of them on there. And then you can also see these nebula. You can also see nebula in there. Now, these are not things where you're going to look at it and it's going to be spectacular, but some of the observing lists have challenge objects on them. And these are sort of like the challenge objects. So if you're looking for a challenge to see something like that, that's pretty difficult to do. You need a pretty good sized telescope, dark skies, and then you have to really be looking for them, and you have to really know exactly how you're going to find them. Okay, the southern, I don't know why this says southern horizon, but Cassiopeia is in the north, and you can see here. Cassiopeia is right in the Milky Way, so it's really in a bright, intense portion of the Milky Way, and so there's a lot of open clusters. There's a lot of other stuff, but you see open clusters are going to really stand out here. So you're going to see, for example, the double cluster. That's a really spectacular object, and it's a good binocular object. And then you've got these other two up here, another pair of I think those are galaxies. And you see 147 and 185. Those are galaxies. And then 103 is also a really nice galaxy. A nice open cluster. Some people have suggested it should be called the 4th of July cluster because you can look at these stars in here, and they're red, white, and blue. So you can see right in the middle, there's a bright red star, and then kind of off to the left side of that little window of the picture, there's another red star, and there's a lot of blue stars in there, and there's also some really brilliant white stars in there. And then the NGC 663 is another one, another object. And then if we look into the southeastern horizon, this sounds like we're going to go back a little ways. These are constellations that are really setting these days. This is coming off of the last month. So like if you go back to August, these constellations were, this is how they looked in August. You can see Scorpius and Sagittarius, and then right above it you see this constellation called Ophiuchus. This is the central portion of our galaxy, and the reason it looks so big is this is like the ball. You know, when you look at a galaxy, there's a central bulge in a lot of galaxies. This is the central bulge in our galaxy, and so that's what you're looking at here. And you can see there's a lot of globular clusters. There's a lot of open clusters. This is probably the richest area of the sky to just sit down with a pair of binoculars or a low power telescope and just poke around and look at stuff. This is where you're gonna get the most bang for your buck. You can see how packed in these things are. Like if you look if you look at the yellow circle there, that's Sagittarius, and right above that, starting with that peak of Sagittarius, there's kind of like, it looks like a teapot, and the very peak of the teapot in there, you can see there's a globular cluster right next to that. But then you can just go from there. You just follow. There's just a line. You could just go up from there and just see one thing after another. There's just a whole lot of things, and you don't need a large telescope to do that. You could do that with really just a finderscope or a pair of binoculars, and you can have a really good time just looking around up in there. And okay, and this is exactly what I was saying. This is the brightest spot in the Milky Way. And when you see pictures of the Milky Way taken in the summer, it is invariably this part of the Milky Way that they're taking, they're showing you in the picture. So here's some more objects that are in Sagittarius. You can see M8. M8 is probably the most spectacular of these objects. It does not look red when you see it through a telescope, but you can see all of that nebulosity there. With I'd say maybe a 10 or 12 inch telescope, you can see all that nebulosity. Even a 6-inch telescope will show you the part that's kind of pinkish white. You could see that stuff in there. The Trifid is also a nice object. Again, it doesn't look blue and it doesn't look red, but you can definitely see it. The part that is red in this picture is that's the brightest part. So when you look at it, that's the first thing you'll notice. But you can't see the blue spot, the blue area off to the left there. And then because this is near the center of our Milky Way, there's globular clusters everywhere. Actually, I think M11 is an open cluster. M28 is a globular cluster. And then Antares. Now we're kind of going back. These stars are really setting for this time of the month, for this time of the year. But it's still a nice area to look at. Antares, you can still see Antares in the evenings, but I think it's getting close to the horizon here. Antares means rival of Mars. Ares was I think it was the Greek term for Mars. And so Antares against Mars is what that means. And then you can look at the other constellation, the other things in here, M6, M7. M4 is right next to Antares. So if you can find Antares, you can find M4. It's almost in the same field of view. And this is also a very rich area. Another thing you'll see is Rho Ophiuchi, which is just above Antares. In fact, people will show pictures of this and they'll call it the Rho Ophiuchi Nebula. And it's invariably it shows Ares in the picture, Antares in the picture. Anyway, I think we're going kind of backwards in months now. So I think that's about it. We're going to call that quits for me. And
Oh, you don't want to go anymore?
no, I don't want it. I don't think so because I just kind of feed back into previous months, and we're getting into stuff that's already set for mid-September.
Okay.
But anyway, that gives you kind of an idea. And then the other thing that we do in the SIGs, once we have gone through this is the first 10 or 15 minutes of the SIG, and we answer questions. Then what happens is people will bring up, they'll either ask questions, or they've got new equipment they want to share with everybody, or people have new stuff that they're working on. They want to talk about stuff that they're working on. But anyway, it's just kind of a good chance to ask questions. And if you're new, or if you have a new telescope, when we start meeting again, what people would do is they would bring up their telescope and we would show them how to use it. So if you have questions like that and you want to meet somebody, or you want to come up here and have someone show you how to do stuff, that's a good opportunity for doing it. Anyway, I'm going to hand it back to Michael here.
Okay. Does anybody have any questions either in the chat or here in the room for Don? Yes.
Yeah.
Okay, when you start having these, meetings back over here at the Bron Observatory, are you gonna still have the Zoom meeting?
I think we are committed to having Zoom and in-person meetings like we're doing here tonight. I think that works really well. I think for a lot of the Zooms, it works really, really well. Can they hear me?
Yes.
It works really, really well to do it by Zoom only. We don't even, I mean, the imaging SIG and the advanced project SIG, I think that works really well when everybody is by Zoom, because people can, it's easier for them to share stuff. It's easier for everybody to communicate. The Zoom stuff works really well. But I think for the beginner SIG, if there's interest, I think we should probably start meeting back up here again, but maintain the Zoom component so people, we have a lot of people from out of state that are coming to these meetings. You can look over here right now. We've got people from South Alabama, and we've got people from Tennessee that can access our meetings because of Zoom now. So I think all of our meetings are going to include Zoom. I can call them hybrid meetings.
I have a question, Don. Yeah. How does one join the beginner's SIG?
That's a good question. If you go to our newsletter, which you may not get, but I'm assuming that most of the people here know that are on our mailing list. Every month we put the links in there to join any SIG meeting. All you have to do is click on that link, and there's no need to join. You just click and join the meeting, and that's it. You don't even need to be a member, so anybody can join. Yeah.
Dallas asks, any recommended apps for beginners on what to observe visually and when?
That's a good question. I'm not really prepared to answer that with slides or anything right now, but I did a presentation about 1.5 years ago about electronic aided astronomy. And basically all I did was, the whole presentation was about apps. You can go on to, I don't know whether you have an iPhone or not, but if you go out to the App Store or whatever it is for your phone, typically you can get Sky Safari. Sky Safari is a very good one. I think there's a free version of it, so you can get the free version, or you can pay $3 and get the slightly better version, and you can pay, I think it's $30 and get the full-on version with 2.5 million galaxies, and I think it'll fly rockets with that one.
May I add on to that? I personally, this is Michael, by the way, I personally use Stellarium for my work at the Space and Rocket Center, which is a free program to use online. You can download it as well as use it just directly on the web. So I highly recommend that one for beginners. And I'm gonna type it in the chat.
Stellarium and it's beautiful.
It's open source.
Beautiful.
It is open source. Thank you, Kevin. Cartes du Ciel. CL, sorry, that as well. Now there was
a good one too. It's not as pretty, but it's free and it's got more technical stuff.
And John, okay, moving on to the next question. John Barry asks, where is the 0 hour relative to Pegasus, for example?
You want to know the right ascension? All of that. Is that what he's saying? And Andromeda, the 0 hour goes right through Andromeda. But if you want to, Well, I don't know how to answer that question. It goes through Pegasus. I don't know what to say. NGC 1, 2, and 3 are all in Pegasus. So that's where the 0 hour right ascension is going to be. It's right near there.
Okay. Does anybody else have any questions? Oh, John Barry asked, how do you look for it?
I would, if you have an app, John, here, just unmute him. Just let him ask.
John.
That's him right there.
Oh, duh. Oh.
Unmute, John. There we go.
Yeah,
What is it?
yeah, well, yeah, I'm just wondering if you had a favorite way to try to find it.
To find what?
You know, I can find it on Stellarium, but is there some particular bright star that you go to first to sort of orient yourself for where 0 is?
I don't know why I would need to know where the 0 hour is in right ascension. Does it matter?
No, he said no.
Okay.
Okay. Let's move on to the next. Jeff, do you want to take over from here?
Yeah, I can go next.
Okay. You have been made co-host.
Let me start up something here. And then I'll share screen. Okay, Don asked me to talk about the Swanson project that we've got going on. And the project that we're undertaking, actually, let me go somewhere else. Oops, let's see. Should have had all this up. So we're undertaking a major project to improve the drive system of the Swanson telescope. So up to now, we've had a robotic system, but it's been an open loop system. That is, the computer really didn't know where the telescope was pointing. We would point the telescope at a star and tell the computer, okay, we're currently on this star. And then the computer would say, okay, if you're on that, then I know how to take you to the next target that you want. And if anyone ever pushed the telescope or anything like that, then the computer would lose track of where it is. So we'd have to go to a known star again and kind of restart. Consequently, the pointing accuracy of the Swanson was not real good. We would typically, even though it was computer controlled, a go-to telescope, we would typically have to star hop. We'd have to go to a nearby bright star for some faint target, like a galaxy or star cluster. We'd go to a nearby bright star and then synchronize on it, and then go the short hop to whatever our target was. It's a bit of a pain, and then so pointing accuracy was not real good, but in addition to that, our tracking accuracy was not great. We had really two types of error. We had a periodic error in the gearing system because we were using motors that go through complex gearing system, and it would tend to cause stars to kind of go back and forth in
Hey, Jeff.
the field.
Hey, Jeff.
Yeah.
We're getting a lot of feedback from your microphone. Do you have something like a fan or something on in the background?
No, but I noticed my, oh, let me try that. Is that any better?
Not at
I
all.
noticed, yeah. I'm sorry, this is going to be, let's see. Let me check and make sure what audio I'm going through. How about this? Can you hear me now?
That is way better. Thank you, Jeff.
Yeah, yeah. I did have it on the wrong, it defaulted to the wrong one. It was not using this. Okay. Yeah, so I was saying, in addition to the pointing accuracy problems, we had tracking problems. And so in order to overcome the pointing accuracy and tracking problems and improve ease of use, we undertook, and you can see this is, we began this in 2019. So we did over a year's worth of design effort, and then started, I believe, last October or November, maybe it was last November, we started disassembling the Swanson mechanics. I do want to show this. This is CAD model. Okay, now I'm getting feedback.
Don,
I'm sorry.
Okay. Yeah, so this is a CAD model, and this is an assembly with, I don't remember how many total parts, 50-something parts that I made. And you can see the various components of the system. The main thing that we're doing is replacing, you may remember we had a big wheel that had a wire drive over here, and there was gearing and motors over here. And all of the gearing is going away. We're adopting direct drive motors, and that's what these two components are. These large, these are, large direct drive motors, so there are no gears, there's no backlash possible. They're extremely high torque motors and able to hold position quite well. And then the other major component that we're adding on are these encoders up here. So the encoders are not part of the motor. In the old system, there were encoders built into the motor, and that's why, and the motor pushed through a clutch system. So if I pushed on the telescope, it would, the motors wouldn't move, but the telescope would move. So the encoders couldn't tell the computer that the telescope had moved. But these encoders, one there, and then, let's see, it's actually in here, yeah. These encoders are absolute, and they are extremely high precision. They're actually, the way they work is the outer band of this has a type of barcode on it all the way around, and then the read head, which, sorry, this is the read head for the encoder, is actually a little camera. It's a little optical reader, so it just looks at that barcode, and it can tell absolutely what position the telescope is in, one for each axis. At this point, so we if you want to keep up with the progress that we're making, we have been posting videos to YouTube. And each video is typically about 7 to 10 minutes long, includes an introductory section, and then we do time-lapse photography of the actual work that we do on the telescope. And so we have about 2 to 4 hours of work that gets compressed down to about a minute, where it looks like we're a bunch of ants running around inside the observatory. And then at the end of the video, then we say what we've accomplished and what we need to do next, or what we didn't accomplish in some cases. At this point, we have mounted everything. All this stuff is, all the mechanical components are mounted, and it is now time to transition and start wiring up the motors, encoders, and hooking that all to the controller. And the controller that we're using, let me increase this a little bit more. So this is the controller that we're using. It's made by the same company that made the controller that we used before, a company called SciTech, Sidereal Technology. But we're using this Force One controller, and it is made for direct drive systems. And we've been in contact with them on a couple of occasions, and they've guided us through some of the engineering problems that we needed to address, but primarily in choosing which exact motors and which exact encoders to get, because the manufacturers of those motors and encoders, there's a huge range of motors that we can purchase. So we had to purchase motors that would deliver sufficient torque for our needs. Another thing that we're adding on to it is a GPS time server, so that we'll get we can keep up with the exact time. Here's a picture of the encoders. It's a company called Renishaw, and this is the edge, the outer band of the ring, the encoder ring. And the encoder, I believe we got the 200 millimeter, roughly 8-inch diameter. So we're able to get, it has inherent resolution, incredibly precise, but really the in situ goal is going to be somewhere around better than I think we're trying to shoot for about 2 to 3 arc seconds in pointing accuracy, which would be far, far greater than what we've had. I mean, it's hard to even say what we had, because there were times when we were degrees off, and there were other times when we were minutes off under the old system. Repeatability was not a part of the old system. And yeah, these were the motors. We got these. This series was the series motor that we got, the KBM motor series. These are the company that makes these is a German company called Cole Morgan, and this was the specs on what we purchased. So at this point, we also had to have quite a few parts manufactured, like all of the motor mounts. The motors, they're called frameless motors because they don't come with any kind of mounting frame. So we had to design and manufacture the frames, and we got manufacturing donated primarily by Teledyne Brown, but also by DSC Technologies up in Tennessee through Lonnie Puderbaugh. He knew those guys. But all of these metal components that are used to, mount the encoder rings. So the rings are truly rings. You can see they're just rings. So we had to mount them on a disc and then mount the disc to a hub and, connect the hub to the axis. This right here is a brake system. So we have to have a brake system on both right ascension and declination axes, because when the power to the motor goes off, all torque disappears. So there's nothing that would hold the telescope in position. So what we're doing, and sorry about that, my mouse is kind of going back and forth on me. What we're doing is we've got, this is actually just a standard car disc brake, and then we're mounting, we're using magnetic door locks, like often at corporate offices, you'll go up to the door, and if you have a card key access, you can push on the door and it'll open for you. Otherwise, you push on it and it won't open. And that's a magnetic door lock. And that's what this little block here represents, is that magnetic door lock. We're using it in a very different way than it was designed, because we're using the friction of the magnet against the brake disc to induce torque, a force, to slow it down and hold it steady, basically. And we've got one on the deck. As it turns out, we are not going to be using a car brake disc on the deck, but rather we're going to be using one of the counterweights itself. The car disc isn't really adding anything. It is a counterweight, but it's not as good of a counterweight as the counterweight. And we need this linear space, the space on the shaft. We do have a shaft extension not shown here that the counterweights go on. So the brakes will actually be on all the time. And once we turn the system on to activate the telescope, then the brakes will go off and the motors will engage. And it turns out that even if the brakes fail, if power goes out to the brakes, there's residual torque in there's enough friction on here that, things aren't going to go flying around, in other words. But having those brakes will stop any motion that the telescope may have due to imbalance. And that's really the only kind of torque that, if the telescope is perfectly balanced, there is zero torque at rest. But that's never the case. And the larger the scope, the more of a problem that becomes. So at this point, I've been working primarily with Mimo DiMartino. If you watch the videos, he and I are typically in all of the videos, not every one of the videos, but and then Logan Curtis has been helping out quite a bit. And then recently, Chuck Lewis came on board, and Chuck is an electrical engineer, and he came on just in time because we are currently in transition to wiring this thing up. And Chuck just produced a couple of wiring diagrams this past week, and we've ordered the appropriate cabling. Another problem that we had in the old system was that every 2 to 4 years it seemed, oh, let's add another cable for this, let's add another cable for that. Because originally our system was completely analog, and by completely analog, I mean that we had analog video, no digital communication whatsoever up to the scope, and we had 3 cameras on the scope, so we had 3 separate analog cables for video. Then we went to a CCD camera. So then at that point, we did go digital. So then we added another cable for digital communications and left all the old cables there. So our conduit started getting more and more and more stuffed. So one of our goals now is to eliminate, in fact, we've eliminated all the wiring at this point, and now we're only going to have power cable. So we will have 110 up to the telescope, and then we actually have a computer on the telescope, on board the telescope. We have a computer there, and the reason for that is to minimize the cable lengths, because the camera communicates by USB cable, and we can't send USB all the way down into the control room. And basically, we operate the telescope that's on the, we operate the computer that's on the telescope through remote desktop, just through the internet. So we have an internet, we have a network cable, we've got power cable, and then we are going to have to route some of this cable. Actually, not the RA, only the deck. So we'll have to route the deck motor cable, brake cable, and encoder. But for that, we don't need heavy duty cable. We're going to be using primarily Cat5 for encoder communications, and then we have a 16 gauge 5 lead cable for the motor wiring, and I believe we may be using it for the brake as well, but I'm not sure exactly. Anyway, I can't give a completion date for this because every month we still have 1 month to go. That's the way engineering projects are. And of course, the pandemic did interfere. We did have a fairly aggressive plan initially, and we're going to have several teams of people working, but it's turned out, largely through most of fall and winter, it was primarily just 2 people at a time to limit risk, COVID risk. But now we're doing a little bit more. So yeah, that's the status. We're ready to start wiring this thing up. And right now, instead of the actual telescope would mount here, and instead of the telescope being there, right now we have counterweights to represent the mass of the telescope. Because when we start to test this, we really are unfamiliar with the system, and we don't want it to basically fly off and throw the scope into the floor or something like that. So we're just putting a dummy weight on it, and once we get everything wired up and start to test it, we'll be able to test it fully without having the scope on it. And once we're comfortable, then we'll mount the scope and start using it. One of the recent milestones we had was Chuck I just realized I forgot the name of that program. Chuck, if you can unmute, what did we use to align the scope? We did polar alignment.
Yeah, it was, oh gosh,
Now you're forgetting. To
I am too. Senior
yeah,
moment.
so
Sharp cap.
okay,
Sharp
yeah,
Cap
sharp
Pro.
cap. So we simply mounted a small telescope. We literally used C-clamps to mount a small telescope to the mount, and then used a program called SharpCap to do polar alignment. And we got it aligned to within less than what was it, 3 minutes of arc?
Three arc seconds.
Oh, arc seconds, yeah. Yeah, I mean,
Pretty
we
close.
were right at 0. I don't have the bolts shown in here, but this thing, yeah, I've got a couple of the, yeah. So like this is a bolt and this is a bolt. And then there's bolts that go in these holes on either side. So the the north end of the pier, this mount is adjustable up and down and east and west. And that's what we use to adjust it. It was fairly aligned to start with. I don't remember exactly how far off it was, maybe less than a degree or right close to a degree.
Oh yeah, it was just a few minutes here and there.
Yeah. And
the nice thing is the Sharp Cap does this so quickly that if in the progress that we're going to make in the next several months, if we knock it out of adjustment for some reason, it's really easy to go back in and within an hour or so, even including all the setup, we can get it back where it needs to be really quickly.
Yeah, it was really a beauty to use. I was quite impressed. And I guess that's it for me. I'll take any questions if anyone has any.
1 second there, Tim. So we have 2 questions that are in the chat there, Jeff, if you could read them. And also there's a lot of really good information from George. So take a look at those and answer.
I'm not sure I can read. Can you read them out to me? Because
oh yeah, okay. Let's see. Rod asked, what is the projected cost to convert them out?
Yeah, altogether it is approaching 15,000. I believe that we had an initial outlay. Let's see. I thought we had, no, I have a separate spreadsheet. Yeah, here we were estimating somewhere between 11.5 to 21. And we did an initial outlay of about 13,000 and then had to come back and request another like 1,500 or so. So it's approaching 15,000.
Okay. Dallas asked, what kind of telescope will it be mounted? What type of telescope?
Oh, well, it is the same Swanson telescope that has always been on it. I don't have that, included in this CAD model. I have kind of a, let's see, I don't, I had, that may have been in here. Anyway, it's our 21-inch telescope that was designed and constructed by members in the 1960s. It's a very good scope, actually, and in particular, we believe that this will become a very good scope for spectroscopy. It's a Newtonian configuration, and for photography, Newtonians are not the best. We've got coma out at the field, and it's an f4, so it's a relatively fast Newtonian, and coma, is greater the shorter the focal or the lower the f ratio. And we do have a focal corrector, a paracore coma corrector. But yeah, so the scope roughly looks like this. This was just kind of an envelope. It doesn't actually look like that because it's an open truss, but this was just modeled to do an envelope study, motion study, actually. I think that may be over here. Oh no, that's another thing. I'm sorry.
That's okay. We have another question here
Yeah.
from John. Will the controller be able to take input from a guide camera in concert with the absolute encoder?
Yes. Yeah, certainly it will. And, we will probably use that kind of configuration most often, or maybe not most often, but anytime we're trying to do long exposure photography. So most often I would say we're probably not going to be using a guide camera because our typical use is on Saturday nights after a planetarium show where we operate a Malincan video camera. And, we want live images to be shown on the screen and fast, going from one target to another, ability to move from one target to another and hold on to those. But yeah, absolutely, we'll be able to do guide camera feedback.
Okay, and Tim, you said you had a question. Please speak up for him.
Yeah, it's 2 questions. if you don't mind.
Yeah, you just speak up for him so he can hear you now.
Okay, the first question is, you said that you start off with a video camera. What do you know? What type of video camera was that?
The old video camera, the original, the first camera that we used on this telescope. It wasn't the very first ever used, but when we made it a robotic system, was a Stellacam 2, and that's just analog video.
And what was the other one, Tim?
I was wondering if you could explain how does a direct drive system work?
How does a direct drive system work? If you didn't hear that, Jeff.
Yeah, so all direct drive means is that the motor drives the axis directly and not through a gear system. So anytime you've got a gear system, you're going to introduce errors of various sorts. You're going to have slop in the gears, the teeth will not mesh perfectly, and there will be, a little back and forth because of that. So that's one type of error. Another type of error is that gears are never perfectly circular. So you tend to get periodic error, which is a sinusoidal error, where the gear may go faster at one point and slower at another point. And we saw that kind of error in our system, and that tends to make stars kind of go back and forth such that the average position of the star is right. In other words, the mount will track the star real well, but it'll have little bloated stars that are actually short little lines because you've got error going back and forth. Now you can take out a lot of that stuff with software, and we did attempt to take out some things with software, but at some point, if your mount's not really good, there's a limit to what software can do. What we would tend to get, because there were times when we actually did use a guide camera. So the guide camera would monitor the star, and as the star moved off position, it would send signals to, reposition the mount back, put that star back in the middle. But what that means, the star has to move off its center, off its position for the, computer to recognize it needs to correct for it. So what happens is the star dances around and becomes bloated. So instead of a pinpoint, it becomes a circle. And we would see that in our images.
Hey, Jeff.
Yes.
Yeah, this is Chuck. Just another attempt to answer what I think maybe was part of the original question. That we think of motors as running constantly, spinning. These motors are motors, but they're really, really slow. So these motors, even though they're called motors, they're running at sidereal rate. So it's a motor, but it doesn't really spin. It just moves very, very, very slowly without any gearing at all.
Yeah, good point.
I have a question. If the motor's running at sidereal rate, how does the brake system work?
The brake system only comes into play when we turn power off to the motors.
Okay, so when the motor is tracking the star, the brakes are off.
That's correct.
Okay, thank you.
Yeah, it's just that the motors lose all torque instantly when you power off. So if there's any imbalance in the telescope, it would just flop around.
And since there's no gear system, there's no mechanical disadvantage that acts as a brake. In that case, it's whatever friction is in the bearing is all you've got at that point.
Tim asked about slewing.
Oh, I'm sorry, I couldn't hear.
Slewing.
Slewing.
You said the motor runs at zero speed.
Yeah, as Chuck mentioned, these motors will primarily run at sidereal rate, but these are actually industrial motors that are designed to run at several thousand RPM. So we're really holding them back. Yeah, we can go whatever rate we want to go, and we're not going to want to go very fast. You know, maybe I don't know, a few degrees per second max, but we get to set that rate.
For that motor to go.
Quite a range if you didn't hear.
Yes.
Tom, you had a question.
Question for you, Jeff. Given that the motors can slew at whatever rate we really need, will the controller have enough flexibility to track non-stellar objects such as a comet?
Yeah, good question. And the answer to that is also yes. Yeah, that controller, we can feed into it. I mean, so first of all, we will actually be using something like Cart de Ciel or, you know, some other user interface program. And it's an ASCOM, the controller takes ASCOM and another standard, and I forget the other standard it takes. I'm familiar with ASCOM. And so basically, it's going to be the end controlling software that determines whether we can track a comet or not. And the answer is yes, we will be able to track satellites, comets, all kinds of things. I mean, yeah, we've never really been able to track satellites because of the speed at which those things move, but we should be able to track even satellites if we wanted to, near Earth objects, things like that.
Would we be able to take a picture of the ISS?
Conceivably, yes.
Cool.
Jeff, do you have any hard limits set up so that you can't drive the scope into the ground or something?
Yeah, currently we don't have any hard limits, but that's something that we want to put in before it's all over. We're really not completely sure what what envelope that we want to allow and what we want to restrict. So yeah, that's something to be done in the future. But that's a good point. Yeah, we don't want this thing driving the scope into the ground.
Okay, I got a question from George. Are these stepping motors? If not, what's the tech? What is the precision of the motors? You would want sub-arcsec control, and I'm having some trouble understanding how they might work.
Yeah, okay. So I am going to, these are not stepper motors, and I'm going to let Chuck tell more about them. But they're three-phase motors, is that right?
Yeah, they are. And I was afraid that question was coming, and I have to admit, I have not dug into that very much. They are three-phase motors. The software is and hardware in that controller is managing current to those three phases through a set of three gates that are software controlled. And I don't know whether that answers your question or not. I need some time to dig into that a little bit too. If you want to learn a little bit more about it, and I'm not sure you can from the website that I've seen, but Cole Morgan has a pretty extensive website. If you want to look up Cole Morgan and search on direct drive, what's the designation for that?
These are KBM series.
KBM, yeah. The specs are in there. I think,
But you might want to just
you've
look
got
up.
you've got the resolution on the motors down there somewhere, don't you?
I'm not sure I've got resolution.
Well, that's okay.
But
Either one of you, Chuck or Jeff, could you post in the chat if you do find that website for George? Is there any more questions from either the audience or from the people online?
So I have a question about dome rotation synchronization. Will the dome be synced with the scope?
that's not part of this project. But yeah, we've talked about that, and you know, I'm kind of two minds on this. I don't see it as a super high priority, primarily because we don't really intend for this to be operated remotely, in the sense that, you know, you can sit at home and open the dome doors and do everything from through the internet. So we'll always have operators present, at least for the foreseeable future. And then if we are in the midst of an exposure, doing a long exposure, rotating the domes imparts vibration into the system that is unwelcome. And so if dome rotation, with the current motors that we have that are rotating the dome, they they really kind of jerk when they start turning that dome. So, I mean, in general, I feel like I want to be in control of when the dome moves, when we make an adjustment. But yeah, we've talked about a variety of systems using motors hooked up to, and then have, basically, we could paint our own system or just have a strip around the edge of the dome, and a camera that monitors it, and Raspberry Pi kind of interface, or some other Arduino type controller or something like that. But yeah, Logan Curtis at UAH, he's offered up 2 or 3 concepts for this, and at some point we'll probably do something, but it's not part of this project.
All right, thank you very much, Jeff. That was very in-depth and very informative. Thank you very much.
Okay. I just posted the Cole Morgan web link to the chat.
Oh, thanks.
So who is up next? Rod, are you ready?
The astrophotography SIG?
Oh, you want to do
Oh,
it?
Joe couldn't- let
Joe, you want to do it?
Sure.
All right, give me 1 second. Let me
Go
make
ahead
you
and share.
You are now a co-host. You're in charge.
Excellent. Okay, yeah. So my name is Joe Kuttner. I'm one of the coordinators of the astrophotography SIG. You know, astro and photography, probably familiar, maybe not familiar together. It's basically a group of people who are cheating the system. We are cheaters. We're using technology to make observations of the night sky. Now you might think, you know, telescopes, that's technology too, but we're doing something particularly sacrilegious. We're not allowing that light that's worked so hard to get across the galaxy or across the universe into our God-given eyeballs. Instead, we're using electronic instruments and taking pictures to see things that you wouldn't be able to see otherwise. Actually, you could see them because you could look at the same picture. It's fun, and we don't have to apologize for it. We just like doing it. So the members of the SIG have mostly have their own setups. They vary from telescopes upon telescopes upon telescopes that guide telescopes so that other telescopes can take images. And these are largely a collection of cables. And most of us spend more money on cables than we do on telescopes and cable management. But the hobby can actually be pretty accessible. So on the right here is a system similar to something I travel with, which is a simple DSLR, 120 millimeter lens, and a special mount that helps correct for the rotation of the Earth so that it can take longer images. And something like this is not very expensive, and as I'll show in a moment, very powerful. So the hobby can range from the god-awful expensive to quite accessible. We also have some members who have their own domes and probably their own spending problems. I think Rod, who's here, has his own. This is not a picture of his dome, but he has his own. And we also have members who rent out telescopes. So they're not even touching or seeing the telescope that they're using, but they might be in a remote location like West Texas, and then you operate it and control it from your home and can get really good results like that. So if you get our newsletter and you see images on the front or later on, like this example from Tim of the Orion Nebula, those are images that we've taken ourselves and have processed ourselves and are really glad to share. So you'll see them in the newsletter. We also share on AstroBin, which is a popular website for sharing images and finding images. I use Flickr, and I'll show you some of the work I've done. I am by far not the most capable of the members in our group, but I do spend enough money to get some decent results. The reason I want to show this is that many of these images are taken with a lot of those different systems. So we've got, you know, I think this was taken with an 8-inch Cassegrain type telescope. Some of these other ones were taken with a much wider field, the 120 millimeter lens on a DSLR, like I showed. But even this one here on the left is just a regular camera with no tracking, no regular exposure. So astrophotography can run the gamut from high power, you know, magnification to just casual images of the sky. Also taking images of very bright objects that don't require long exposures, like the moon. This is I think a total lunar eclipse, don't remember exactly. And then other objects require much more significant power to magnify. So I was going to show some of the software that we use, but I had some technical issues. So I quickly pulled up a YouTube video of one of the pieces of software that we use to process our image. This is called PixInsight. So after we've collected data from imaging through a telescope and into a camera, we'll open many individual subframes, as we refer to them, combine them using a stacking process, and then process them with some more advanced tools in this software. So let's see if we can find an example of what's going on here. In this case, this person's pulled up an image of the Andromeda Galaxy, and it went away. As you can see, some of these images start out maybe with too much noise, or in this case, you can see I think this is called vignetting, where it's like darker in the corners, but there's a circular, brighter area. And some of that can be removed. So it does require some software to get the nicer images that we have. There's a fine line between art and science here, though. I think most of us, stick to enhancing the data we have versus adding data or anything like that. So yes, if you'd like to join us in the astrophotography SIG, we meet on the second Friday of the month, 7:30 p.m. We also have a group me, and I think the easiest way to join that is just to send me an email at jpkuttner@gmail.com. I think if you give me your phone number or a group me username, I can add you to the group. We have a variety of skill levels from the very, very advanced to the very beginner, and are always happy to help people get started with astrophotography. Yeah, so I'll turn it over for questions or for whoever's next.
Yes, thank you, Joe. Does anybody have any questions for Joe? Going once. Going twice. 3 times. Okay. So I believe Rod is our last up. Rod, are you ready to go?
I am ready. I actually don't have any slides or anything to present, but the Advanced Projects SIG meets on the 1st and 3rd Wednesdays of each month. We start a little bit earlier. We start at 7 o'clock instead of 7:30, but the login is the same login that you'd use for any of the Zoom meetings with VBAS. We started talking about spectroscopy, and we went through some RSpec demonstrations and how to use that. And since then, Mel Blake from the University of Alabama in Florence has loaned a spectrometer to us, and Eric has been working with that. So I'm going to briefly turn it over to Eric, and he might have a few things to show and tell.
Hi, good evening. So nobody was playing around with the spectrometer, so I volunteered to give it a go and see what I can do with it. And so I've had it for a few weeks now, and haven't gotten on a telescope yet. I'm just familiarizing myself with it. It's about a $4,000 spectrometer here. So if you see on top here is where the light path comes in from the telescope. The light would then go down here to a mirror, go through a collimating lens onto a grating, which is back in this portion here. And the tilt of that grating is controlled by this micrometer. And then it goes back through another collimating, or the same collimating lens, and out to either an eyepiece or a camera here. It also has a port on top here where you can look through at the slit itself. The slit where the light goes through has a mirrored surface and is angled at about 10 degrees, so that you can actually get an image, take an image of that and make sure that the star that you want to look at is actually the one that's on the slit. And so you can see the reflection of the rest of the light that's getting in from the telescope, and make sure in your star field that you're looking at the right object that you're trying to see. So far, I've only played around with it to kind of get to know it. And if I can share briefly, let's see, share screen. So you should see some images that I took. Just to get familiar with it, I put a LED flashlight on the entrance port, and to make sure the light is actually getting down to the camera. And I used a microscope camera that I had around the house to take some images. And it's this spectrometer's got a 2400 lines per millimeter grading in it. So it really has pretty high resolving power. According to the documentation that comes with it, it's about resolving power of 1800. And so that micrometer that I showed you, where that tilts the grading, that needs to be moved through 20 full turns to get all the way through the visual spectrum. So it really does have a quite a good resolving power for you to see pretty finely spaced lines in the spectrum. So you see here, we got about 20 pictures at the different micrometer settings that go all the way from the, the deep blue into the red. So like I said, I'm just kind of getting familiar with it. I can see that, it is working. I'm not sure the alignment is the best. As you can see, the images are not, the light is not fully filling the frame of the CACD. So I'm gonna play out with the alignment some, and then I'm gonna try to take some solar spectra and see if I can actually see the lines in the absorption lines in the solar spectra, and then try to calibrate it. It does have a very, I'm gonna go back to stop the share here. How do I do that?
Should be up at the top of the screen.
Oh, there it is. It's somehow jumped over to my other monitor. Okay. So let's see, where was I going with that? Oh, so yeah, you've got this micrometer here that actually tilts the grading in there, and it's about 20 turns to get through the whole visual spectrum. So should be able to resolve some good lines in the solar spectrum, the absorption lines. It also has a flat lamp in it, so that you can take flat field photos for image processing later on. It also has a calibration lamp. It's got a argon neon lamp, I believe, in it. It's not a super bright lamp. It's like a very small lamp inside, not as bright as the kinds of things you had in chemistry laboratories. So I don't get a lot of photons registering on my camera, but I need to play around with that a little more and see if I can't, with a little better collimation, get a sharper images there. So like I said, it's a lot of fun. I'm just getting to learn it, and read through the manuals, and think I understand it fairly well now. It's a matter of tuning it up and actually putting on a telescope and seeing what I can see. But as Jeff Delma said earlier, it'll be very nice to get this thing on the 21-inch telescope, because when you're dealing with dim objects, they talk about potentially needing up to an hour of exposure time to do a single image. And as I said, if it takes you 20 turns of the micrometer to get through the whole visual spectrum, you can only zero in on a small portion of a star spectrum if you're going to take an hour for each image, right? So there's trade-offs in spectroscopy. The main one being that once you start splitting light up into a spectrum and looking at narrower and narrower portions of that spectrum, there's less and less photons that are going to make it through your spectrometer and onto your camera. So bigger apertures up to a limit are helpful to make your data collection fast enough for you to be able to really get something meaningful out of it. And it totally depends on your application. The applications they talk about in the literature that comes with a spectrometer are things like, one, solar spectra, obviously, two, looking at various star spectra, see if you can determine spectral types on stars, watching the evolution of variable stars over time. There's, American variable observers are looking for that kind of data for certain stars. You could also look at the rotation of Jupiter and look at the Doppler difference from the leading and trailing edges according to what they've gotten lit. So pretty interesting and versatile instrument to play around with. So I'm having fun playing around with it, and glad for the opportunity to actually get to play with somebody else's $4,000 instrument that I didn't have to buy. So hopefully Mel will let us use a little bit, and then once we get our 21-inch up and running, we'll be able to help him with and his students with research up at the observatory.
Thank you, Eric. That is a scientific grade instrument. I mean, you can really produce actual science. We measure the rotational velocities of galaxies. There's a lot of things you can do with it. So thank you for that report. Another thing that we've been talking about in the advanced project SIG is photometry, how to measure the magnitude brightness of a star using differential photometry. I have been taking some courses with AAVSO. Once you become a member, the courses are very, very inexpensive. It's $35 for a course. And you can learn all types of things about photometry, including in-depth information about how CCD cameras work and why it's important to take all of the calibration images we do, and the importance that it makes on being able to actually make accurate measurements. You can be able to determine the color characteristics of stars. So it's an interesting project to get into. And actually the information that you gather in photometry, you can submit it to the AAVSO database, and other scientists can actually use your information as they study the variableness of stars. One other thing that we've talked about a lot is with ham radio. We had some ham radio operators present some information to us, how they can actually detect meteors. And basically the way I understand it, you have some VHF stations that are always transmitting a signal, and you set up a receiver at some point, and you just constantly listen for that frequency. And they have special software that can detect when, in an instant, in a flash, you can actually detect that particular carrier due to the signal reflecting off a meteor that has ionized the atmosphere. So there's some interesting things that we talk about. I don't know if advanced is really the correct term. It's really different types of projects involving astronomy that don't involve the visual or the astrophotography aspect. So we have a good time. And again, we meet the first and the third Wednesdays of every month at 7 o'clock. Are there any questions?
Tim has a question.
Well, you probably can't see it, but I brought with me something I made at home, an equatorial platform. It was I don't know if this would pertain to the advanced project SIGs or not, but what I brought here actually put on a dome and tracked the sky with for about an hour. And the reason why I brought that up is that from time to time we talk about doing things like teaching people how to build their own telescopes, even grinding glass to make it into a mirror. I don't know if you put that in the advanced SIGs or not, but
Tim, why don't you pick it up and show it?
oh, okay, sure. I'll show
Here's
you.
the camera,
But
Tim.
really, I brought it more as an example of what I was wondering if we would go into.
Yeah, I already did.
All right. Here it is.
So
You mind moving around
the
just a little bit?
telescope would sit up here.
Yes, the telescope would sit up here and it would just move around. You could slide it a little bit.
It was like that. So it simulates a polar axis.
Yeah.
By doing that. And so Dobbs don't normally track the stars. And so if you're looking at things with high power, they go out of field of view very quickly. But with this, it will stay in the field of view.
Yeah, it's not really active for anything like astrophotography. Although if I work on it some, I might be able to get to where I can do lucky imaging for planetary. But I was hoping in general that maybe over time we could start developing more DIY projects for VBAS.
I have a couple of comments on that, and just in general, telescope making is something that I've always been interested in. I ground a 10-inch mirror and constructed. I've got several Frankenscopes scopes that have been cobbled together from various parts over time, and it's something that I would like to, at some point after the Swanson is up and working, I would like to do some sort of mirror grinding or telescope making class, or get a group of people who are interested in that kind of thing. It wouldn't have to be the same for everybody. Maybe somebody wants to make a 10-inch and somebody wants to make a 6-inch or something, but I'm definitely interested in that kind of thing.
Or make something that's not readily commercially available, like an F3, something like that.
Yeah, but you're talking about grinding lenses. Is that what you're talking about?
No, for the primary mirror.
Right.
Yeah, mirror, not lenses. Lens making is far more complicated than mirror making.
I meant grinding your own optics.
Yeah.
Which a lot of people might not realize we can do. Amateur.
Very much.
Yes, but even if people aren't interested in grinding their own mirror, they may be interested in making their own telescope or making things like what Tim made there, that equatorial platform. Or, I've made little camera, what do they call those? Barn door camera mounts. Yeah.
Yeah, until recently, when you had the COVID shortages, you could go to some websites and you could actually buy an already made mirror.
Right.
So all you have to do is to make the rest of the structure, which, the hard part is the mirror itself. Once you get past that, everything else is a lot easier.
And Jeff, I don't mean to interrupt you, but would you like to plug your class here? You're teaching a class in a couple weeks.
I am teaching a class called Practical Astronomy, starts the 27th, and you can look in the Via Stellaris to learn more about it. It's an 8-week course, I believe $25 for members, and it's an observational astronomy class, and it's primarily about learning the basics of how to go about learning to observe and learning to find things, and how to read star charts, and basically how to know where things are in the sky and locate them in your telescope. You don't have to have a telescope to attend the class. There will be some society scopes and some of my own scopes that I bring up for others to use. But if you do have a telescope, you're highly encouraged to bring that. And in fact, we'll be able to house a certain number of telescopes for the duration of the class.
Jeff, can people attend your class by Zoom?
Not this year. No, I did that last year, and because it is practical astronomy, it's divided partly lecture, and then we go outside. And I did it all by Zoom last year, and it was good. It was well received, but I tried doing some observing nights, in the mix of it. I think we had 3 or 4 observing nights, and only a few people were able to attend, and it didn't work out real well. So each, I believe we start at, I can't remember, I think it's 7 o'clock. Monday the 27th is the first class, and lecture. Well, the first night's lecture I know is a little bit longer than most of them, but then after the lecture, we go outside and start using telescopes. But I mean, there are 8 sessions. One of the sessions is on astrophotography. One of the sessions is even on radio astronomy. Not so much that you will do radio astronomy, but just for you to understand that visual astronomy is such a teeny tiny portion of what astronomy is all about. And the vast majority of research work is done in radio, the super broad range from centimeter to kilometer wavelength.
George asked if we'll touch other areas such as X-ray, gamma rays, etc.
Certainly, I think as people who want to talk about those things and discuss that, they should definitely join the SIG.
Okay. Well, we are now hitting the 1.5 hour mark. Does anybody have any last minute questions? Okay, we need to wrap up.
Yeah, I don't have a question, but I have a plug as well. It's not a SIG or anything like that, but public outreach is something that we've still been doing to a limited extent during the time of COVID. And for instance, I volunteered to do a class for the Boy Scouts on observing. This was for the Boy Scout leaders up at Camp Comer a few weeks back. And those kind of things are very rewarding, because when I'm preparing to do something like that, I learn 10 times more than what I would learn if I was just doing something for myself. It's a lot of fun, and also observing events when we go out and I think we're starting up the Saturday night observing events again, even though we're not going to do planetarium shows. It's a lot of fun. You really don't need to know anything much to be able to show the stars to somebody. If you can point the telescope at a bright object in the sky and know, it's a planet, and you can use your cell phone to with one of those free apps on it to tell you that, or work with one of the other people up there. It's a lot of fun to be able to show somebody Saturn for the first time, or another object, even the moon in the telescope for the first time, and then things like giving presentations or signing up to do a planetarium show in the future when we start those up. I learned so much from doing that. And if you look up something on Wikipedia 5 minutes before you go outside with that telescope to show to the public and tell them, yeah, that star cluster is 140 light years away, they will be very impressed. You may forget it the moment you walk away from that telescope too, but they will be very impressed, and they will learn something, and they won't remember that fact either, but they'll say, wow, I saw something really cool on the telescope. It's just a lot of fun, and you get to talking with people, and I'm not even a people person. So I just encourage people to don't be afraid that you have to be some kind of master astronomer who's done everything and knows everything about everything to go and show people the stars.
My introduction to VBAS was when I was a sophomore in high school in Huntsville, and I happened to go up to one of those Saturday nights, and if I recall right, we looked at the moon.
Sometimes it's the only thing we can see from up there.
Hey, Eric, this is Kevin Lofty. Real quick comment. There's a documentary called Saving the Dark. It's about light pollution in America. It's a great documentary if you want to spend an hour watching it. but they're talking about community outreach, things that you can do in your community to raise awareness and spread the word on, the possible solutions to light pollution in your vicinity. So it's called Saving the Dark, and I can recommend it.
Thank you, sir. So we have one last question, and then we're closing. We're closing. Okay.
I got one too.
Are there going to be any new sections in your class, Jeff?
No, there's no new sections. But I have one question for everybody or anyone, and that is, why do they call them microwaves if they're centimeters wavelengths?
Don't think about it too hard.
Hey, I
got-
have an announcement I'd like to make to the group, if I might take a minute there.
Go ahead,
Wayne.
Wayne. What you got?
Yeah, Wayne McCain. I'm a long-term family member. I just don't get to come over to the activities very much. We live over in Athens. But anyways, I wanted to just make note, and I can share a screen on it here if that's okay. Okay, I guess I can't. So anyway, Mel Blake is also working with us on this, but several years ago, we made a presentation, I believe, to the VBAS about a small CubeSat radio astronomy project that we were working on. And that has not gone away. As a matter of fact, we signed an agreement and have a launch date now for fourth quarter of 23. We're working with VBAS Space down in Cocoa Beach to launch the satellite. We're working with Calhoun and just lots of other collaborators. Dr. David Fields, who runs the observatory up at Roane State College near Knoxville, is basically the principal radio astronomy, principal investigator. But we would love to have someone here local, some group of people who may be interested to participate if any of the VBAS people are interested. It's called the STEMSat-1, and I'd be glad to send a little PowerPoint PDF on it if anybody wants to know more about it. That was all.
Wayne, I'd like to invite you to the Advanced Project SIG, and you can make a presentation to us.
I'd love to do that. Yes, sir.
I will say our next meeting is going to be in October. Let me get the date. It'll be October the 1st. No, I'm in the September. I'm in the wrong month. It'll be October the 6th. And I do have a conflict for that day. I haven't talked to you, Don, about it, but I am not going to be available on the 6th to host that particular SIG. So I'm probably going to need some help from someone. But yes, Wayne, we'd love to have you present, and we'd like to learn more about that project.
All right. Excellent. I'll be there.
Yeah, Rod, just remind me the week prior.
Okay.
And if nobody else can do it, I'll do it. It's not a big deal. Also, I never got a chance to say that the beginner SIG is the first Friday of the month. So we've got basically we've got the first Friday is the beginner SIG, the second Friday is the imaging SIG, the third Friday is this, what we're doing right now, the meeting. The fourth Friday, we'll give you the fourth Friday off. And then the first and third Wednesdays at 7 instead of the others are 7:30. The first and third Wednesdays are 7 o'clock. So we hope you guys can join us. You don't have to do anything. You can just turn off your video and listen if you want. You don't have to join in. But we hope you guys can join us. And it's a lot of fun, even if it's over your head or you think it's going to be over your head. You can still have fun just kind of eavesdropping and finding out what other people are up to.
And with that, we are going to close this meeting. Thank you very much for attending, those in person and those on Zoom. You had fantastic questions. Thank you, everybody that presented, and we will see you next month. Bye-bye.
Thanks, everybody.
Bye.
Goodbye.